In this lecture video, we'll be looking at Spearman's rank correlation coefficient for the nonparametric assessment of the relationship between two variables. Now let's first review the Pearson correlation coefficient. As you learned in one of your previous statistical methods courses, the Pearson product moment correlation coefficient, hereafter called the Pearson correlation, is used to assess the nature and the strength of the relationship between two quantitative variables. It requires data at the interval level or higher and has the specific interpretation that it measures the strength of the linear relationship between the two variables. The Pearson correlation between two variables at the population level is denoted by the lowercase Greek letter rho. The Pearson correlation between two variables in a sample is denoted by the lowercase Roman letter r. Inferences about a population Pearson correlation rho are made by its point estimate, which again is r, as well as by confidence interval estimation and hypothesis testing. Now let's think about how we interpret the Pearson correlation. The Pearson correlation coefficient takes values between -1 and +1. Again, the correlation is always between -1 and +1. Now this is an important point to keep in mind. If, when you are calculating a correlation coefficient, you obtain a value for the correlation that is outside of this range, either less than -1 or greater than +1, then you can know for sure that you've got a calculation error, because mathematically, based on how the Pearson correlation coefficient is defined, it can be shown, it can be proven mathematically that it's always going to be between -1 and +1 inclusive. Now again, interpreting the Pearson correlation, the sign of the correlation indicates the direction or the nature of the relationship. On the other hand, the magnitude of the correlation quantifies the strength of the linear relationship between the two variables. A positive correlation indicates a direct relationship between the variables. That means that as one variable increases, the other variable tends to increase as well. That is, the data points tend to follow a trend line that has a positive slope. A negative correlation indicates an inverse or negative relationship between the variables. This means that as one variable increases, the other tends to decrease. That is, the data points tend to follow a trend line that has a negative slope. Now let's talk about quantifying the strength of the linear relationship. A Pearson correlation of 0 indicates no linear relationship at all. Now, that doesn't mean that there's no relationship at all. It means that there's no linear relationship. That's one thing we need to keep in mind when we think about the Pearson correlation, is that it is measuring a very specific type of relationship, a linear relationship. So a correlation of 0 indicates that there's no linear relationship at all. Now, a correlation of +1 indicates that a perfect positive linear relationship exists between the two variables. In this case, the relationship between the two variables is deterministic. There's no random deviation from the line relating the two variables. All points fall perfectly on a line of positive slope. Now, similarly, a correlation of -1 indicates a perfect negative linear relationship. In this case, again, the relationship is deterministic in the sense that there is no random deviation from the line. All points fall perfectly on a line of negative slope. The strength of the linear relationship becomes stronger as the correlation gets further away from 0 and closer to either -1 or +1. Conversely, the relationship becomes weaker as the correlation gets closer and closer to 0. Now let's review how the Pearson correlation is defined and calculated. And so to do this, we'll need to introduce some notation for the data that will be used to calculate the correlation. And so when we are talking about a correlation, and talking about a relationship between two variables, we have to have a set of bivariate observations or a bivariate data set. And so we will denote these bivariate data points or bivariate observations as ordered pairs, right? And so the first variable will be denoted using the letter X, and the second variable will be denoted by Y, and then we'll subscript each of those to indicate the observation or the experimental unit or subject upon which those measurements are made. So X1, Y1 is the first bivariate data point or the bivariate data point measured on the first subject. X2, Y2 is the bivariate observation measured on the second experimental unit, and so forth up to X sub n, Y sub n, which is the observation measured on the nth experimental unit. And so we have this bivariate random sample of size n. The Pearson correlation coefficient, expressed or defined in terms of these observations, is given here. So the sample correlation coefficient, you can see here, is the corrected sum of products of the x's and the y's. So the sum I going from 1 up to n of the product of the centered x values and the centered y values. And when we say centered, we mean that we've subtracted off the mean of the particular variable. And so that's the numerator of the correlation coefficient. The denominator is the square root of the corrected sum of squares of the x's times the corrected sum of squares of the y's. So that is how the Pearson correlation coefficient is defined. Let's talk about some characteristics of the Pearson correlation, some sensitivity issues in particular. So there are a few problems associated with using the Pearson correlation as a measure of the relationship between two variables. Because of how the Pearson correlation is defined, as we saw on the previous slide, in terms of the products of moments, its value can be greatly affected by extreme and or influential values in a sample. Now, this is the same issue that plagues the mean as a measure of location and the variance and standard deviation as measures of variation. You'll recall from your first methods class, when learning about the mean as a measure of location and the variance and standard deviation as measures of variation, that those measures were very, very sensitive to extreme values. If you've got a single extreme value in a data set, that can really, really impact the mean of that data set. It'll pull the mean in the direction of that extreme value. And in addition, because the variance and the standard deviation are based on sums of squares of deviations from observations from the overall sample mean, that squaring of those deviations really, really impacts the values of the variance and the standard deviation when you have even a single extreme value. So that same kind of problem impacts the Pearson correlation as a measure of the relationship between two variables. Now, another issue is related to inference about a Pearson correlation at the population level. So hypothesis testing and confidence interval estimation procedures for the Pearson correlation are based on an assumption that the underlying population or distribution from which the sample is obtained and about which inferences are to be made, the assumption that that underlying distribution is normally distributed, and in particular in the case of two variables, a bivariate normal distribution. When this assumption is not met, then that negatively impacts the validity of these inference procedures. It negatively impacts the validity of the hypothesis tests in the sense that p-values may not be accurate because those p-values are based on, again, this assumption that the underlying distribution is bivariate normal. And it can also impact the confidence interval estimation procedures in the sense that the coverage probabilities being something different than 95%. So there are some issues related to the use of the Pearson correlation coefficient, both in terms of how extreme values can impact the value of a correlation coefficient in a sample, as well as inference procedures about population correlation coefficients. The underlying theoretical framework for the Pearson correlation coefficient is bivariate normality. And again, you'll remember that a normal distribution is symmetric about its mean. And so deviations from that kind of assumption impact negatively the Pearson correlation, and inferences drawn from a sample Pearson correlation and about a population Pearson correlation. Now, let's also look at some applicability limitations of the Pearson correlation. One other problem in using the Pearson correlation is that it is designed for use with data at the interval or ratio level. So you'll recall that those are the two highest levels of data. You've got 4 data levels. You have the nominal level, which can be used to identify, but for which there's no natural ordering. Then you have the next higher level, which is ordinal data. That's data where a natural ordering exists, but differences between values are not defined or are meaningless. Then you have the interval and ratio levels. Those are the 2 highest levels, and those are the levels for which the Pearson correlation coefficient is defined and for which it has meaning. And the meaning is very specific, as we've indicated. The interpretation of the Pearson correlation is that it is measuring the strength of the linear relationship between 2 variables. And in order for the Pearson correlation to have that interpretation, the 2 variables have to be at either the interval or the ratio level. You can have both at the interval level, you can have both at the ratio level, or you can have one at the interval and one at the ratio level. That's fine, but both variables have to be at least the interval level in order for the Pearson correlation to have this interpretation of being a measure of the strength of the linear relationship between the 2 variables. But variables at the ordinal level can also be related, and so with that in mind, it still makes sense to seek to understand the direction and to quantify the strength of the relationship between 2 variables at the ordinal level. When you have that situation, the Pearson correlation coefficient, as it's interpreted, would not be applicable. So now let's look at overcoming these sensitivity problems and applicability limitations by looking at what is called the Spearman rank correlation coefficient. The Spearman rank correlation, hereafter called the Spearman correlation, is defined for data at the ordinal level or higher and has properties similar to that of the Pearson correlation. So it's got similar properties, but it does not have all the properties because it has broader applicability. Now let's look at the similarities. Specifically, the Spearman rank correlation is always between -1 and +1, as is the Pearson correlation. And the stronger the relationship between the 2 variables, the closer the Spearman correlation gets to either -1 or +1. The closer the Spearman correlation gets to 0, the weaker the relationship, the farther away the Spearman correlation gets from 0, and therefore closer to either -1 or +1, the stronger the relationship between those 2 variables, even at the ordinal level. But because the Spearman correlation only uses the ordinal level aspect of the data, it's no longer specifically a measure of the strength of the linear relationship between the 2 variables. So in order for the Spearman correlation to be applicable to ordinal level data, it can only use the ordinal level aspect of that data. So even if you've got data at the interval or ratio level, you can utilize the Spearman correlation with that data. But keep in mind that the Spearman correlation is only going to use the ordinal level aspect of those interval or ratio level variables. So there is a sacrifice of some information when using the Spearman correlation with interval or ratio level variables, but there are some advantages to that, and one of those advantages would be robustness. All right, now let's look at the notation for the Spearman correlation. So you'll recall that the Pearson correlation coefficient at the population level is denoted by the lowercase Greek letter rho. The Spearman correlation between 2 variables at the population level is denoted similarly, but we subscript rho with S for Spearman, obviously. And we do the same type of thing with the Spearman correlation coefficient between 2 variables at the sample level. We use the lowercase Roman letter r as we did with the Pearson correlation, but we subscript it with S to indicate that this is the Spearman correlation, not the Pearson correlation. All right, so let's now look at some advantages and disadvantages of the Spearman correlation. So there are advantages and disadvantages of the Spearman correlation in comparison to the Pearson correlation. The biggest advantage is that because the Spearman correlation only uses the ordinal level aspect of the data, it is much less sensitive to extreme and/or influential values in a data set. Now, you'll recall that that was one of the big disadvantages, one of the problems with the Pearson correlation, its sensitivity to extreme values, to influential values in a data set. A single extreme value in a data set can have a huge impact on the value of the Pearson correlation. So that's one of the disadvantages of the Pearson correlation. But the Spearman correlation, because it's not using the attributes of data at the interval or ratio level to differentiate those levels from the ordinal level, it's only using the ordinal level aspect of the data. The Spearman correlation coefficient is not going to be impacted very much at all by extreme values. And that's similar to how the median as a measure of location is insensitive to extreme values, and also how the interquartile range as a measure of variation is also not very sensitive, not greatly impacted at all by extreme values in your data set. So the Spearman correlation, we can consider it as a more robust measure of correlation or the relationship between two variables. It's not going to be as impacted by extreme values or influential values. Now, a big disadvantage of the Spearman correlation as compared to the Pearson correlation would be in terms of interpretability. The interpretation of the Spearman correlation is much less specific or explicit than that of the Pearson correlation. You'll recall that the Pearson correlation has the very specific interpretation, and it's always, when dealing or when using the Pearson correlation, it's always important to keep this in mind, that the Pearson correlation is a measure of the strength of the linear relationship between the two variables. It's not measuring the quadratic relationship or any other kind of relationship. The Pearson correlation is measuring the strength of the linear relationship between the two variables. But because it really does not make sense to speak of a linear relationship between ordinal level variables, the Spearman correlation does not have this same interpretation. And so the interpretation of the Spearman rank correlation is limited to a more vague notion of an increasing or decreasing relationship and the extent to which such a relationship holds between the variables. And when we talk about increasing or decreasing, when we're talking about ordinal level variables, we're talking about increasing or decreasing in rank. Because again, when we're talking about data at the ordinal level, the definition of ordinal level data is that a natural ordering exists and is meaningful, but differences between the different values are not defined or they're not meaningful, they don't make sense. And so with ordinal level data, there's no sense or measure of distance. That notion does not make sense when it comes to ordinal level data. Now, let's see how we calculate the Spearman rank correlation. How is it actually defined? Well, the Spearman rank correlation is actually defined in a manner similar, very, very similar to that of the Pearson correlation. The big difference is that instead of using the original interval or ratio level variables as the Pearson correlation does, the Spearman rank correlation applies the same formula as the Pearson correlation, but applies it to the ranks of the observations in the data set. So to see what I'm talking about, let's again let x and y represent interval or ratio level variables. All right, so those would be the measured variables on each of the experimental units. And then for each I going from 1 up to n, we're going to let cap r sub I be the rank of x sub I amongst just the x's, and we'll let cap s sub I be the rank of y sub I amongst all the y's. And so when we do that, we get a data set, a new data set, consisting of the ranks, and these are ordered pairs of ranks of the corresponding observations. And so that becomes the new data set that we're going to analyze using Spearman's rank correlation. So once we've ranked the x's and ranked the y's, and we do that separately, there's a separate ranking for the x's and a separate ranking for the y's. And once we've done that, then we put those separate ranks back together for each experimental unit or subject, and we get this new data set. And so once we've done that, then the formula for the Spearman correlation is given by this expression here, this formula. And you can see here that really all we've done is we've taken the Pearson correlation and replaced the x's with their ranks, the y's with their ranks, and then the corresponding rank averages. And so the formula is the same, but it's applied not to the original data, but to the ranks of the data, and that's why we call it the rank correlation. Now, when there are no ties in the ranks, there is a shortcut formula available, and this shortcut formula may or may not be useful. It really depends on the size of the data set. If you've got a large data set, then perhaps it won't be that much of a time saver. I mean, if you've got a large data set, you're probably going to be using a software package to calculate the Spearman correlation anyway. And so using the shortcut formula really would not be of any use because the shortcut formula is typically used by hand. And so the primary place or situation where this would be beneficial would be when you've got a small data set, and again, when there are no ties in the ranks. And so when that's the case, when there are no ties, then the Spearman rank correlation can be calculated in this way, where again, n is the number of observations, the number of bivariate data points, and then d sub I is the difference in the ranks of x sub I and y sub I. So specifically, d sub I is equal to r sub I minus s sub I. Now, let me just caution you that when ties do exist in the data set, then this shortcut formula will not give the same value as the Spearman correlation definition formula on the previous slide. You won't get this same value. If you've got just a few ties, then it will more than likely be very close, but it won't be exactly equal. And so if you've got more than just a few ties, then you probably don't want to use this. You probably want to use this formula. But again, in many cases, you would be using specific software, for example, SAS or SPSS or Minitab or R or something like that to calculate the Spearman correlation anyway. Now, let's talk about inference about a Spearman rank correlation. So again, the population level Spearman rank correlation is denoted by rho sub s, and we're talking about this kind of thing in the context where this would actually make sense at the population level. In those kind of situations, it would be of interest to not only calculate a sample Spearman correlation, but to use it to make inferences, to draw inferences, draw conclusions about the relationship between the two variables at the population level using this Spearman correlation construct. And so the null hypothesis would be that the two variables are not related with respect to this Spearman correlation versus the alternative hypothesis that the Spearman correlation is non-zero, and therefore that the variables are related in some sense. Now, determining the reference distribution to use for this kind of a test, and from which we would obtain the appropriate critical points, is very challenging. It requires special tables or software to implement. And so for the purposes of this class, we're not going to try to do this by hand. We don't have the special tables available to us, and those are becoming a bit dated anyway. Typically, people would use specialized software for this. And so when we actually want to test a hypothesis about a population Spearman correlation coefficient, that's what we're going to do. That's going to be our approach. I'm not going to expect you to test a hypothesis by hand about a population Spearman correlation. And so what I will demonstrate in some examples is how to use SAS to perform this hypothesis test to determine if two variables are related at the population level according to this Spearman type of correlation. The specific SAS code to calculate the Spearman rank correlation from a set of data and to perform this hypothesis test is given on the next slide. So again, I will be asking you to calculate a Spearman correlation by hand, the sample Spearman correlation, but I'm not going to ask you to test hypotheses. All right, if we do that, then it would be using SAS software. But I do want to show you how to do this because you very may well need to do this in your own work and research. So how do we instruct SAS to calculate a Spearman rank correlation for a sample? And how do we instruct SAS to perform this particular hypothesis test? Well, it's very, very easy. And This is the SAS code to do a correlation analysis, and in particular a Spearman rank correlation analysis. So the capability in SAS to perform this correlation analysis is contained, it's encapsulated in the core procedure in SAS, so proc core. And in order to get SAS to do a Spearman correlation analysis, we need to give it a keyword, give it an option, and that option is Spearman. And so when you include the Spearman option to the proc core invocation, then this instructs SAS to calculate the Spearman rank correlation and to perform that hypothesis test that we saw on the previous slide. Now let me just also point out that SAS proc core by default will always perform a Pearson correlation analysis, and so you'll see the results for that Pearson correlation analysis in the output. You don't have to add a special keyword or option to get the Pearson correlation, but you do need to issue or include this keyword, the Spearman keyword, if you want a Spearman nonparametric correlation analysis, the Spearman rank correlation analysis. All right, so that is the background and the particular details of the Spearman correlation coefficient. What we'll do next will be to look at examples involving Spearman rank correlation. As we look at these examples, we're going to do the analyses two ways. We're going to use spreadsheet software to implement the formula I showed you and to calculate the Spearman correlation coefficient. In addition, we'll use SAS to calculate the Spearman correlation, and we'll be able to check our work that way. And we'll also use SAS to perform the hypothesis test to determine whether, at the population level, the Spearman correlation coefficient between the two variables is non-zero. We will pick up these examples in the next lecture video.